Hello and welcome to our next video presentation on the theorem of the Pythagoras concept that we have been learning for years and years together. You ask anyone the question on what do you know about the Pythagoras theorem, and there will be at least two common approaches, two common statements that would come from everyone. And they would tell me, sir, the first one is going to be that it is only applied in a right angle triangle because we need a 90 degrees for this theorem. And number two is that the square of the hypotenuse is equal to the sum of the square of the remaining two sides. That is, hypotenuse square is equal to side 1 square plus side 2 square in another approach to put it. But little do we think of how must have Pythagoras actually brought this theorem into account. So let's have a look at some of the basic approaches that must have gone into bringing this theorem. But before that, while you're watching this video, I want you to like, share, and subscribe this channel. And click on the bell icon. Don't forget that because that's going to keep you connected to us. So please do click on the bell icon. Now, as we go further, the right angle triangle, the square of the hypotenuse is the sum of the square of the remaining two sides. So I have given you a right angle triangle, triangle ABC here. And we can see that the hypotenuse AC is, if we square it, it will be equal to the addition or the sum of AB square plus BC square, which is the basic statement of this theorem. So let's take down a few details from this triangle. That I have triangle ABC, and in which I have an angle ABC as 90 degrees. Segment BD is the perpendicular height on side AC, which is my hypotenuse, such that it keeps points A, D, and C collinear to each other. The basic proving statement is all that we got to keep in our mind. AC square is equal to AB square plus BC square. Construction is as we can see it in the figure, and therefore let's start with the crux of the theorem. If we consider the two triangles ADB and ABC, so I'm going to go backwards again, and I'm going to make you have a look at the two triangles that I'm going to be considering in the first round. I'm considering ABD, the smaller triangle, with the bigger triangle ABC. In the second case, I'm going to consider this smaller triangle BDC with the bigger triangle ABC. So, when we look at it, we have that angle A was the common angle between both right on the top. And in this case, we had angle C as the common angle between both. I'll repeat to go back again. I wouldn't mind deferring to go back to show you that A was the common angle between triangle ABD and triangle ABC. While in the second case, BDC and ABC have angle C as a common angle. So therefore, we have these as common angle. We can see the 90 degrees between them, and therefore we can prove them by AA test. Now, if I have, let me highlight this by putting it out to you here, this case and this case, again, like in my previous video on similar triangles, as I said, I love you, you love your daughter, therefore, I love your daughter. That's where we get this concept coming in from. So that proves us from 1, 2, 3, we can say that all the three triangles are going to be congruent, similar to each other, and by the principle of transitivity, we can apply them to the reality to prove the Pythagoras theorem in my next segment. So let's go further. When we took these triangles into account, okay, what do we get? We see that these triangles are very much similar as we just saw. So we prepared the corresponding sides. Remember the theorem of CSST. The corresponding sides of similar triangles identifies that in similar triangles, their sides are always in ratio. And from this, I'm only going to consider two of them into account, particularly those two who have something to do in common. I'm going to look at this something in common, because if I cross multiply, when I cross multiply them, I'm going to get AB square and BC square respectively, as we can see here. If I add them both, AB square plus BC square on my left hand side, AD into AC plus DC into AC on my right hand side. We can take AC common out in both and AD plus DC. If we look at the triangles, we had A dash D dash C. So AD and DC ka addition would be coming up to AC. Therefore, we get AC square. So this is how the whole theorem is approached in a way. And another extension to this theorem would be if I considered again, let's say I'm going to consider triangle ABD and triangle BDC. We already proved that these two triangles were similar to each other. So therefore, what if I do so, that if I put BD upon AD is equal to DC upon BD. Again, as corresponding sides of similar triangles, I can cross over and I will get another very clear statement. Instead of me writing it, I'm going to press enter just there, and there we get it. BD square is equal to DC into AC. This is the concluding statement of the theorem of geometric mean, an extension to the principles of similar triangles and Pythagoras to conclude this theorem. So I'm not going to take into more applications or numerical approaches to Pythagoras because we have been doing them since childhood, but I'm going to take a special video on the applications of Pythagoras for people who want to learn them from basics to the very end of geometric mean and play with it in a little bit of their own comfortable ways. And we will work on that in our next video presentation. So with this, we would like to definitely say a big thank you for spending your time to watch this video with us. And please do not forget to like, share, subscribe to our channel, and click on the bell icon to remain connected to us. I'm going to keep reminding you of that. So thank you so much, everyone, for watching this video presentation.